Hello, everyone, and welcome to the United Nations University Institute for Water, Environment, and Health Science Talk Series. In this, our 30th anniversary year. I'm Abraham Mbogo, UNU Researcher WASH, and I'm delighted to be your host for today's Science Talk. For those of you joining us for the first time, our Science Talks showcase the diverse, policy-relevant, and interdisciplinary research of UNU-INWEH and our global network of experts. These sessions are designed not only to share cutting-edge science, but also to explore how that science translates into real-world solutions for water, environment, and health challenges around the globe. Today's session, like all of our talks, is being recorded. The video will be made available in an open access format following the event. And you can find recordings of all our previous science talks on demand via our website and YouTube channel at unu.edu/inwe/science-talks. As always, we'll conclude with an interactive Q&A session, and please feel free to post your questions in the chat at any point during the presentation. Today's science talk is entitled Spatial Patterns of Groundwater Use and Depletion in Transboundary Aquifers, a new typology of border zone use to identify high-risk regions and guide cooperation. And it is my great pleasure to introduce today's speaker, Professor Marc Müller. Dr. Marc Müller's research examines how water mediates interactions between policy decisions and global change, shaping the distribution of social and environmental impacts across space and time. He works on topics including water and food security, transboundary water cooperations and conflict, and the social hydrology of climate change using methods from geospatial data science, remote sensing, econometrics, and systems analysis. Dr. Müller leads the Human Environmental Systems Group at IRWA, the Swiss Federal Institute of Aquatic Science and Technology, and is also an associate research professor at the United Nations University Institute for Water, Environment, and Health. Please join me in welcoming Professor Müller for today's science talk. Thank you. The floor is yours.
Thank you so much. Thanks for this very nice introduction, and I'm super excited to be here and to present this fairly recent research about transboundary groundwater. Do you guys hear me okay? Okay, perfect.
Yes.
Great. All right, so let's get started then. So when we think about transboundary groundwater, it's very much ubiquitous. There's more than 400 aquifers. As it turns out, there's actually more shared groundwater resources between countries than there are shared rivers. Almost every country that's not an island actually shares some of its groundwater with a neighbor. And in total, the transboundary aquifer account for approximately 35% of all groundwater irrigated croplands and 15% of all irrigated cropland, including surface water. So it's a non-negligible part of global food security that relies on water that are shared between national jurisdictions. What's kind of surprising is that despite the fact that transboundary aquifers are so ubiquitous, there's almost never formal cooperation between countries over the management of these aquifers. So this has been monitored because it is one of the Sustainable Development Goal indicators, namely it's indicator 6.25. And they found that approximately 15%, as you can see on this cake chart, approximately 15% of the aquifer have any cooperation, and of an even smaller amount have formal cooperation specifically focused on groundwater. That would be like a treaty on the management of a shared aquifer. So it almost never happens. What's really surprising is that international cooperation often happens over surface water. So there's quite a few agreements on shared surface water basins, as you probably know. And there's also quite a few ways to cooperate on the management of domestic groundwater. So when you have an aquifer that's been shared locally within a country, there's almost always some institutional mechanism for a joint management of this aquifer. However, in the intersection, that is cooperation over international groundwater is almost never happening. And so it is kind of a puzzling fact. And so kind of what spurred this research was to try to understand what is going on. Why is cooperation, formal cooperation, so difficult to achieve over internationally shared groundwater? So to get started, what we did is that we looked at the few formal cooperation cases that actually do exist, and you see some of them on this map right here, and try to understand what was different in those cases, what made cooperation more feasible or achievable, or perhaps more desirable in these instances. And specifically marking are the two ones that are in bold here. So one on the Genovese aquifer between France and Switzerland. That's actually the only a shared aquifer where there is a binding agreement on volume, meaning that both parties have agreed to limit their pumping to a certain amount of maximum volume per year. The other one, the DC Sakram aquifer between Saudi Arabia and Jordan, here the agreement is rather on where the groundwater is being pumped as opposed to how much. But it is still a binding agreement in the sense that both countries have agreed not to pump within a certain distance of the border. So these are the two binding agreements that we really focused on the initial part of the study. So we published a few papers. I mean, generally what we do is that we combine economic modeling of incentives, specifically game theory, with physically realistic modeling of groundwater flows of the actual aquifer. And this becomes quite complicated. We published a few papers. What I'm going to do within this talk is to really make it simple. So we're going to try to use very simple 2x2 games with very basic groundwater principle to try to understand the dynamics that made cooperation difficult or less difficult in certain instances. So if you're interested in the full papers, they're right here. Also feel free to reach out to me separately, and I'll be happy to send them to you. But here, what we're going to do is that we're going to simplify really the situation. And I really want to emphasize here, this is really a simplified, stylized model to really try to understand the dynamics. So let's imagine that there's two key actors, or two key decision makers on either side of the border. We know, of course, that the reality is more complicated, but for the sake of argument, let's assume there's one decision maker on either side of the border. And let's assume that they could choose between pumping a lot of water, that would be high, H here, or pumping a lower amount of water, that will be L. So again, a very simplified perspective on choices here. And let's also assume that if both countries pump a lot of water, so HH, they make some number, right? So $2 million to 2 units of payoffs, of profits. Now, let's assume that if instead of pumping high on both sides, they pump low on both sides, so they cooperate to some extent by restricting their pumping. Because the marginal utility of water decreases, meaning that the first unit of water that you use is going to be very valuable to you compared to the X units that you've already used. And the water level also will be higher because less water is being pumped. And so both countries, both sides of the border are able to make an increased profits if they restrict their consumption. I mean, that's the reason why they might collaborate and not use too much water in the first place, right? So very reasonable assumption here. And now, of course, if one country decides to restrict their consumption and the other one decides to not restrict their consumption, then we're in a very asymmetrical outcome. And so I call this outcome deception, meaning that one country reaps the benefits of the other country restricting their level of use, so makes 4. Whereas the other country restricts the level of use, but does not reap the benefits of both countries restricting the level of use, so they make 1, right? So in the case where L is the orange country here and H is the yellow country here, the yellow country pumps more water and makes a benefit of 4. The darker country pumps less water and makes a benefit of 1, and vice versa asymmetrically. All right, so this is kind of the basic setup here. Now, if you look at the payoffs, it really makes sense for both countries to restrict their consumption. The total benefit of the system is 3 + 3 = 6 in this case. That's more than any other situation. But if you look at what either country might do, and you put yourself in the shoes of the darker country, so the orange country here, they have to decide how to react to either decision by the yellow country. So if the yellow country decides to pump low, as you can see on the left here, it's either they make 4 or they make 3. So they would choose to make 4 and pump high. And complementary. If the other country decides to pump high, they would either make 2 or make 1. So they will choose to make 2 and also pump high. So the point here is that whatever the other country decides to do, the darker country is better off by deciding to pump high. And since the game is completely symmetrical, the two players are interchangeable, what ends up happening is that both countries will decide to pump high, even though it is not in their final best interest to do so. And this situation is called the Nash equilibrium. And the fact that in this case, the Nash equilibrium, what ends up happening if both countries optimize best on their best response to what the other country will do, ends up being suboptimal compared to what they should decide at the group level, right? So the best situation would be low, but what ends up happening is high. And this is a typical tragedy of the commons situation, also known as the Prince's dilemma. And the idea of an agreement, of course, is to move from the Nash equilibrium, so from the red situation, to a system optimal, so the green situation. So this is kind of the theoretical framing of the problem here. So how do you achieve this? Well, the first thing that you could do is install a buffer zone, right? So restrict the level of interaction between the two sides of the border. So if you do that, then, at the extreme case, if there's no interaction at all, then basically either country can make 3 by pumping low and 2 by pumping high, no matter what the other country does. And you have this kind of outcome matrix. And if you try to solve the Nash equilibrium in the same way that we did before with these change numbers, you end up having the Nash equilibrium actually matching the system optimal, and you have a harmony game, right? Where what ends up happening is the actual social optimal outcome. And this is actually what was implemented in some ways in the DZ-SAC-RAM treaty. So one of the treaties that I described earlier, where both Jordan and Saudi Arabia established a no pumping zone or restricted pumping zone around the border to basically establish this buffer zone that would limit the hydrogeological interaction between the two countries and therefore affect the payoff in a way that is more consistent with the harmony game. Of course, this is a simplified version of it, but the dynamics are very much like that. Now, of course, you could only do this if you have space to do that. So if the aquifer is too small and you don't have enough space to actually establish such a no pumping buffer zone around the border, then it becomes more complicated. And by the way, I forgot to mention, there is the previous game does not imply any binding restriction on how much water is being pumped. There's no such restriction. The only restriction is really on where the water is being pumped, which is much easier to implement. But when you cannot do that, though, like it is the case in the Genovese aquifer between France and Switzerland, then you have to find another solution. And here, really what we kind of think happened is that there was some incentive to make an agreement work, so to say, between France and Switzerland over this shared aquifer, because they were embedded in a much larger kind of system of interaction where collaboration was seen as being beneficial in its own right. And so if you wanted to represent that kind of stylistically in this 2x2 game, you could model it as a benefit of cooperation. So when cooperation is successful, you could, for example, add 2 as a payoff, right? So we have 5-5 instead of 3-3. And so if you change this payoff like this, then obviously cooperation becomes a Nash equilibrium. So 5-5 is a Nash equilibrium. But what's quite interesting is that if you actually solve the Nash equilibrium, there's really 2 Nash equilibria. There's one where collaboration happens on both sides, that's the 5-5, but also one where non-cooperation also happens on both sides. So these are both stable alternatives. And so which equilibrium you end up being really depends on outside parameters, outside dynamics, I would say, and so in this case, trust is important in order to be in the proper equilibrium. More than this, actually, we found in our work in the Genovese that it's really about a Goldilocks zone, right? So cooperation is really possible when water has just the right value. If water is not valuable enough compared to the cost of making cooperation happen, and in Geneva, this could happen, for example, if both sides decide that they don't really care about the shared aquifer, they're really both going to take water from the lake, from some other source, that's much easier to access, right? So if that is the case, if cooperation is too costly compared to the value of the shared water, then we have a reverse harmony game where basically it really makes sense for neither country to cooperate, and both countries are better off by not collaborating. So that would be a reverse harmony game. So this is if water is not valuable enough compared to the costs of cooperation. In contrast, if water is too valuable, so to say, and then there's no room to cooperate. Let's say, for example, that the aquifer is almost empty, and so therefore the last remaining drop of water is super valuable. And in this case, really, you could reformulate that in terms of payoff matrix, and what you end up happening is a chicken game, where although it would be best for both parties to collaborate, really what ends up happening is that you're in the situation where the two countries are running into each other on a bridge, and they're playing a chicken game where the ones who swear it out basically loses, right? But if nobody swears out, both lose, and that would be the 0-0 situation. But in this case, the national equilibrium is that one country uses all the water and the other one does not the other one is basically being worse off, right? But my point here is that if you don't have space to implement this zone-based pumping restriction that I talked about earlier, then you could collaborate in a very restricted conditions where the value of water really matters. It shouldn't be too valuable, otherwise there's no room to collaborate, and it shouldn't be not valuable enough, otherwise there's no real benefits of collaboration. All right, so this is all very, very theoretical. Kind of we use game theoretical argument to try to understand the dynamics of cooperation in existing agreements. But really what we got out of it are three hypotheses that we kind of want to see whether they apply on a broader analysis of groundwater use and exploitation at the large scale, at the global scale, over all transboundary aquifer. The first real hypothesis here is that if the prison's dilemma is indeed a dynamic, so the very first matrix that I showed where both countries have the incentive to use too much water, more than they should, then presumably shared aquifers should deplete faster on average than comparable aquifers that are not shared, right? So this is the first hypothesis that we're trying to test in our global empirical analysis. Then the second hypothesis is brought up by the harmony game. So remember, if you make sure that the two countries are far enough from each other, you could potentially limit this overuse of the aquifer. In other words, if you kind of flip the arguments, the overuse should mostly happen close to the border, right? And this is our second hypothesis, that the depletion or overuse should really be more intensified near borders compared to the bulk of the aquifer, if that makes sense. And the third hypothesis is brought about by this Goldilocks principle that cooperation, when you are restricted in space, could only happen under very specific conditions in terms of water values and trust. This, we're going to formalize it as a hypothesis that formal cooperation is rare, particularly in spatially constrained conditions. So these are kind of our three hypotheses that we're going to try to evaluate using any data that could give us indication on how transboundary aquifers are being used and potentially depleted at the global scale. So talking about these data, so we rely on two main sources of data. The first one is very valuable information coming from approximately 100,000 wells. So this was gathered by Scott Jaseczko and Deborah Peroni in a paper they published in 2024 in Nature. The data is available. And what they did is that they used all these wells from approximately, I forgot how many countries, but a lot of different countries globally. And for each of the wells, they analyze depletion trends, so how quickly groundwater level is changing, so either increasing or depleting over a period of at least 8 years in the early 21st century. Now we use this whole data set. We applied some selection criteria, so the fact that there should be enough wells, etc. Approximately 667 of these aquifers that contain wells pass these criteria. Approximately 40, well, no, not approximately 40 of these aquifers actually overlay with an international borders and are considered transboundary. And so what we did first is that for each of these aquifers, so each of the 667 aquifers, we determine average depletion rates. So in terms of millimeters per year that the aquifer is being either depleted, so that would be positive, or replenished, so that would be negative. So on average across the aquifer. And then the second analysis that we did is we looked at trends against the distance to the border. So we wanted to determine whether the aquifer was more rapidly depleted close to the border. So we regress depletion against distance of each of the wells from the nearest borders. So for transboundary aquifers, well, it's the border that actually intersects the aquifer. For non-transboundary aquifer, we simply took the nearest international borders. So it doesn't overlap with the aquifer, but it's still the nearest one. It's kind of our approach. Then we matched each transboundary aquifer to a non-transboundary aquifer, or rather to a weighted combination of non-transboundary aquifers. And these weights are determined based on covariates or stuff that we could observe that we think could explain potential differences in depletion rates between transboundary and non-transboundary aquifers. We control for this by matching transboundary aquifer to comparable non-transboundary aquifers. So these matching variables are the location, right, to account for any fixed effects due to where the water is being used, at the regional scale, urban cover, so presumably if there's a higher or a lower amount of city covering the aquifer, you're going to use more or less water and deplete more or less the aquifer. Crop suitability, so this is not how much crop is actually being grown there, because this is what we want to get at. However, it's how suitable the climate and the soil and those types of physical conditions are to plant crops. So we want to make sure that the aquifers that we compare have comparable, underlying condition when it comes to planting crops. So everything except for water availability, I guess. And we also match for the presence of a border river, and I'll get to that later in the presentation. And then we do a meta-regression. So we essentially use a regression framework to determine whether transboundary aquifers differ in terms of how rapidly the groundwater is being depleted, or how much more it's been depleted close to the border compared to comparable non-transboundary aquifers. And what we found is interesting. So first of all, we found that on average, the baseline, so these are the matched non-transboundary aquifer, are being depleted, so more than zero, right? So there is a depletion on average of the groundwater in those matched non-transboundary aquifers. But we found that compared to those, transboundary aquifers are being even more rapidly depleted. Not much, but statistically significant. So by about 10 millimeters per year, more than comparable non-transboundary aquifers. What's more interesting, I think, has to do with the border depletion trend. So here, negative means that the aquifer is being more depleted close to the border. So we see that baseline, so non-transboundary aquifer, there's no real significance. So it doesn't really matter how far you are from the border in terms of how quickly the aquifer is depleted. This is expected. If there was a significant trend here, that would be surprising. However, aquifers that are transboundary, we do see a significantly increased depletion close to the border. So this is consistent with this hypothesis that the border actually is a locus of increased groundwater depletion. So that's quite interesting, I found. Okay, this I already talked about. And these results, which are the baseline results of the well study. So these are observed depletion. I want to emphasize that this is actual observation data. They are robust to many different covariate and matching architecture, to sample inclusion criteria, all the kind of arbitrary choices that we had to make to have the model run. We did variations of these choices and found that the outcome, the qualitative outcome, is really robust to these arbitrary choices. However, the key caveats, of course, is that these are 40 aquifers, right? So these are 40 transboundary aquifers. It's about almost 10% of all the population of transboundary aquifers. And so we're not really able to extrapolate that easily to global aquifers. And more concerning, perhaps, is that maybe those aquifers that have well observations are special in some ways, right? Maybe they're more depleted, maybe they're consistently different to these other transboundary aquifers that don't have any wells. And so these are kind of problems that we really have to solve. And so we have to move beyond using direct observation from wells, because these are simply not available for all the aquifers. And now we use a ground cover analysis. So here we try to understand not where the aquifer is being depleted, but where the aquifer is being used. And by use, we mean that we monitor irrigated cropland because the bulk use of most groundwater at the global scale comes from irrigated cropland. So we have very good data on irrigated croplands at the 1 kilometer scale globally. We have some idea of where the water is coming from in terms of it being either groundwater or surface water. And we have some global hydrological models that allow us to determine whether this area is water scarce or not from the blue water perspective and green water perspective. What we did, though, is that we still wanted to kind of apply a comparable methodology. So we wanted to look at patterns of irrigated croplands overlaying transboundary aquifers and compare that to patterns of irrigated cropland in domestic aquifers. Now, the problem is that we don't have a data set of domestic aquifers. We don't know where these are generally. So we did the second best thing, and we took topographic basins. So oftentimes, aquifers kind of follow topography very broadly. And we know that there's a big uncertainty on this, and so we applied essentially a Monte Carlo to kind of get a handle of the uncertainty. And so what we do is that we essentially, for each transboundary aquifer, we generate an ensemble of potential non-transboundary controls, right, in order to have really a distribution of effects for each aquifer. Long story short, so we looked at two measures. We looked at the proportion of the aquifer that's being covered by irrigated cropland. So this is irrigation coverage or irrigation intensity. But we were also interested in whether irrigation has a tendency to be more predominant closer to the border, right? That's the second hypothesis. And to measure this, what we did is that we used a Gini-like index. So Gini is usually used to measure economic inequality. Well, here we use it to measure spatial inequality, so to say, right? So if you plot cumulative land areas against cumulative irrigation area in terms of distance to the border, you could determine whether irrigation tends to happen closer to the border. So that would be like the curve A here, the red one with the negative Gini. And if it tends to happen rather closer to the bulk, that would be the blue curve here. If it's completely uniform, for example, as happens in the Indo-Gangetic plain, where irrigation is really happening all over the place, then Gini basically follows the diagonal. So these are kind of our metrics here. We did the analysis, again, the same thing. We determined the extent to which, so the proportion of domestic, so matched domestic aquifers that are being covered by irrigated crop, and it's about 2%. And this distribution represents uncertainty associated with the control that I talked about earlier. And then we determined by how much more was our transboundary aquifer covered by irrigated cropland. And we see, as you could see here in the golden distribution here, that it is statistically significantly more than incomparable non-transboundary aquifers. So transboundary aquifers tend to be more irrigated than non-transboundary aquifers at the global scale. That's kind of the gist of it. They also tend to be more overdrafted. And here we look at situation where the water used by irrigated cropland is more than the recharge of the aquifer based on global hydrological data. And we see that the situation where the aquifer is presumably depleting because too much water is being used tends to occur more predominantly in transboundary aquifers, which is consistent with them being more rapidly depleted, which is the results of the wells analysis. What is interesting is that when you further control for river borders, it turns out that this explains quite a bit of the increased irrigation in transboundary aquifers, meaning that perhaps one of the reasons why there's more irrigation in transboundary aquifers is because there tends to be more rivers. And the reason why there tends to be more rivers is because oftentimes rivers are themselves international borders, right? So maybe it's the other way around, right? Maybe geography makes it so that transboundary aquifers are excessively used compared to non-transboundary ones. So that's kind of a hypothesis here. We looked at spatial patterns, right? So the box above is really about average use, and now we look whether irrigated cropland tends to be even more predominantly located close to the borders. And we find here, again, same as with the wells analysis, we find that for domestic aquifer, there's no real pattern, which is expected, right? So it doesn't really matter how far the border is in terms of explaining where irrigation happens. However, for transboundary aquifer, it does matter. So it seems that similar to the well depletion, irrigated cropland tends to happen closer to borders in transboundary aquifers. That's what you see right here, right? So it's a negative significance effect. However, this effect disappears when you control for rivers, which means that the reason why irrigation happens close to borders in transboundary aquifers is because these borders are often overlapping rivers. Again, it's the same hypothesis as earlier. So maybe geography really explains why transboundary aquifers are being increased, used in excess close to borders. However, what's interesting is that if we differentiate groundwater from total irrigation, so if you look at specifically the irrigation that's being sourced from groundwater as opposed to surface water, then you see something slightly different. You could see that when you further control for rivers, it really doesn't affect the situation, meaning that groundwater irrigated crops tend to be closer to borders in transboundary aquifers. And when you control for rivers, that stays like that. So it is not the fact that a river coincides with the border does not explain the fact that groundwater tends to be predominantly used close to borders in transboundary aquifers. All right, so that was a bit fast, I apologize, but a quick kind of overview of the results here. Transboundary aquifer depletes faster than comparable non-transboundary aquifer. This is the wells result analysis. Its depletion near borders is increased compared to non-transboundary aquifers. So the wells say that depletion is more rapid close to borders in transboundary aquifers. And this is confirmed by analysis over irrigation, using irrigation cover over all transboundary aquifers. And we found that river border geography, you could see an example of it here. So this is the Amut area, which here is makes the border between, I think, Uzbekistan and Turkmenistan. And you could see that this is where irrigation is happening, right? So this is one of the hypotheses. But if you look at groundwater specifically, it does not explain everything. So there seems to be a residual tendency to use groundwater close to borders when you look specifically at groundwater irrigated crops. Now, a key caveat is that these are global average results. So every aquifer is unique. And so the next question is, how policy relevant is that actually? And so the last part of the analysis here is that we looked at all these aquifers and we identified which ones of them really are being used close to borders. And we could see that it's very, very heterogeneous across all the aquifers. Specifically, a whole bunch of them are not being used nowhere near the border. So these are so we have approximately 500 dyads. So these are pairs of countries sharing aquifers. And approximately a third of them don't use the water nowhere near the border. So they use the aquifer, but beyond 100 kilometers of the border. And so presumably there's no real transboundary interaction for all those aquifers. And these are, for example, large desert aquifer like the Nubian aquifer in East Africa, or other very, very big aquifers. A whole bunch of them also don't use groundwater near the border for irrigation. They use them for cities, right, that oftentimes overlap the border, but not for irrigation. A very small amount of them use all the water within 10 kilometers. So these are small aquifers that are very, very heavily used, very, very close to the border. So presumably these are flashpoints. An example of those are the aquifers that are shared between the Palestinian territories and Israel, for example, where a lot of the water being used is really used close to the border. And generally, there's very few instances where agreements actually happen over those aquifers. And finally, the remainder are being used kind of both near and far from the border. And these include the DZ aquifer that I talked about earlier. And these, I believe, are low-hanging fruits for cooperation where you could actually implement zone-based agreements. Last analysis we did is that we looked at future potential use. So here we looked at cropland that is not currently irrigated, but that is water scarce. So presumably they will be irrigated in the future. And here you could see that the two categories that really increase are these flashpoints. So a lot of flashpoints are there's going to be way more flashpoints and way more instances of aquifers that are being completely used within 10 kilometers of the border. And to some extent, also more of these low-hanging fruits and fewer of these urban-only shared aquifers. All right. So key findings again, these are we talked about, the fact that transboundary aquifers are more intensively exploited and depleted, particularly close to borders. Hydrogeography is a thing, right? The fact that alluvial and river corridors tend to coincide with border, that's certainly part of the explanation, but it's not all the explanation. So it's possible that the dynamics that I talked about earlier in the show also play a role. The implication, transboundary interactions matter. So it is worth putting efforts in policy to develop sustainable cooperative management on these aquifers. What's quite interesting is that most of the action really happens close to the border. And so this focus, this new focus on zone-based governance, so the fact that you don't look at the whole aquifer as a monolith, but really split the aquifer in different zones that should be subject to different governance approaches really makes sense to me. The other very important thing is that cooperation may be more tractable than expected, because if the reason that people use the aquifer close to the border is because the river is there, that's much easier to manage than if they use it, it's because of the incentives that I talked about earlier, because if I don't use it, the other guy is going to use it, etc. So these kind of demand-side incentives are much more difficult to manage than simply the fact that the aquifer is being used because a river is there. So this is somewhat encouraging, I find. And finally, the fact that the river, border rivers actually matter in terms of aquifer depletion is also a signal that surface water, groundwater coupling really matters. You could see it as a challenge, of course, but you could also see it as an opportunity because there's many cooperation frameworks that happen over surface water, and these could be leveraged and extended in order to cooperate over groundwater. And finally, not one size fits all. So many transboundary aquifers are really highly heterogeneous. Many of them actually don't have any transboundary interactions at all. Some of them have a lot of interactions. So all this to say that it's not a one size fits all, and you really have to focus on the specific local context to come up with the best policy to address cooperation. All right, so this is it from my end. I would be happy to answer any questions that would come from the audience, either online or in the room at INWEH. Thank you so much.
Okay, thank you so much, Professor Müller, for this insightful presentation. We'll now move to the Q&A session, and I'll start the interaction by asking this question. You said transboundary water depletes faster, and looking at the current political conditions, what do you think is the future of transboundary water? Maybe if some countries are extracting more along the boundary because of political reasons.
Yeah, I mean, that's an excellent question and a very difficult one to answer. What I think is important, that our empirical findings really show, is that political reasons may not be the main reason why transboundary aquifers are being used close to borders, right? We just showed that geography is really a critical factor. The fact that borders tend to often overlap with rivers, and irrigation tends to happen close to rivers. And this was a surprise for us. Like we expected, political reason or incentives reason or stuff like that to really play a key role. But when we found that simply if we control for river location, then the effect essentially disappeared. At first, we were a bit more concerned. We're like, okay, maybe this is a boring story, but I don't think it's a boring story. I think it's an interesting story, and potentially an encouraging one. Because if really the river is the reason why people use, or countries tends to overuse shared resources, then there is a way to focus transboundary governance, right? Let's manage this river properly. Usually there's already frameworks to do so. Let's extend those frameworks to groundwater, and maybe we will solve many of the potential issues. We won't solve all of them because the political aspects that you describe probably do happen, but we could already solve many of them, I think, by simply focusing on geography.
Okay, thank you for this response. And last week, we learned that innovation is not enough when it comes to water security. So still on the transboundary corporations, do you think the corporations will be enough, still looking at the differences between some of the countries that you cited in your presentation?
Yeah, that's also a very interesting question. I mean, it depends what the objective is, right? So the DC aquifer, one of these shared aquifers that are often brought as an example of cooperation, is particularly interesting because it's a desert aquifer. So it's not like the aquifer is being used sustainably, right? It's not being replenished, and so the aquifer is being depleted. And so here, I think the goal is for the aquifer to not be depleted even more because it is shared, right? So I think you really kind of have to set your objective, right? I'm not saying that cooperation between countries will produce a sustainable management of shared water every time, but I'm saying it could produce a better or a more sustainable or least unsustainable or less unsustainable management of the shared water than if they were not cooperating. And I think that's the objective here.
Okay, thank you, Martin.
Thank you, Mark. Very, very interesting presentation. So based on this analysis, if we want to promote a collaboration framework or cooperation framework, what would be the criteria for establishing framework for collaboration? For example, when two countries do this kind of treaties or on the surface water, they establish on the basis of the water level or discharge on the river. So in case of aquifer, what would be the basis of cooperation and treaty if you put, and how that would be monitored in terms of establishing that the treaty is working?
Yeah. So this is my take on it. I think that really with groundwater, so with rivers, you always have an upstream and downstream. You always, it's everybody sees the river. It's kind of more clear how you should even get started in collaborating. And it's less clear for groundwater, and maybe this is one of the reasons why cooperation is more difficult. But I think what the study has revealed is that you really have different regimes or different types of aquifers. So for example, I talked about the many aquifers who are not used at all near to the border. Those, for example, maybe cooperation is less difficult for those, right? Because nobody uses them close to the border. So let's just agree to have a platform to talk, right? Without any binding restriction on how much water is being used, etc., right? Because there's no real transboundary interaction. And this is, as a matter of fact, I think what happens in those agreements on very large desert aquifers. Now, in other cases, you use water near to the border, but you could also use water further away from the border, and that's what happened in the DC. And so here, maybe I would argue that space is key, right? So you really establish different zones that are close to the border. You establish a certain regulation, maybe on whether or not you're allowed to pump. So this is more easy to actually verify, right? You could see cropland and not. But maybe if you're far enough from the border, it doesn't really matter, right? And so you could kind of say, okay, let's take it easy on the restriction on this shared aquifer if we are, 100 kilometers of the border or something like this. And this is what happened in the DC. Now, if you don't have the space to do that, then it becomes more difficult. And here you really have to go the old way with trust building and having like a joint commission and stuff like that. Much more complicated. But in those specific aquifers, which are a minority, I think, then it's worth kind of going the extra mile and having a tailored solution for this problem, I think.
Thank you. So do you think from your analysis, extensive analysis of all these aquifers, we can come out of a kind of policy framework to initiate this kind of discussion for maybe promoting a framework for transboundary aquifer collaboration and transboundary aquifer?
I mean, I'm hopeful, right? So there's two ways. There's two outcomes of the studies that I think are valuable in that sense. So the fact that surface water, groundwater interactions really matter kind of puts way in the kind of impetus to use existing river basin organization and surface water cooperation framework to kind of expand to groundwater. I think that's super valuable. And the other benefit, I think, is to really show, as I just said, that you know, that different aquifers requires different types of cooperation, and not all of them require the full-on, you know, full monitoring and full restriction, right? And so maybe this divide and conquer kind of approach, that some aquifers, maybe we could be more relaxed about cooperation, could perhaps help, right? It's kind of divide and really focus efforts on these aquifers that are really critical and hotspots, so to say.
Great.
Okay, thank you, Müller. I'm just wondering, in your tracking, did you consider rates of recharge as well, you know, to balance, you know, the expectations, you know, around cooperation?
So you're talking about the theoretical model or the empirical analysis?
Well, both ways, you know, because once it comes to groundwater aquifer, you know, the moment you start talking about depletion, it makes sense to balance it with recharge if it's going on. Because if research is going on, it changes the dynamics. If there's no recharge at the same rate as depletion, it changes the dynamics. You know, so did you throw, you know, that into you know, your considerations? Yeah.
So in the theoretical analysis we did, I didn't show that because I focused on the 2x2 game, just to kind of give an idea of the dynamics. But in the actual models, we actually accounted for all the fluxes and stuff. For the empirical analysis, for when it comes to wells, we didn't really need to look at recharge simply because we directly measured depletion. So we actually had observation of how deep the groundwater was and how quickly it was, you know, these depths was increasing or decreasing. And so we already measured what we were interested in. We didn't need to simulate it using use and recharge, right? So that's for the wells analysis, which only concerned 40 aquifers. For the global analysis using irrigated croplands, we weren't able to account for it directly because we didn't use a fully specified, you know, groundwater balance model for each aquifer. That was too complicated. But what we did is that we kind of accounted for that in terms of accounting for overdraft. So we had a global model that determined whether the water being used are being needed by the crops. So, you know, you have a crop model, some with certain needs for evapotranspiration. Some of it is provided by rainfall, some of it is missing. And so we determined whether this missing water was more or less than the recharge. And that gave us an idea of the overdraft. And we did the analysis on overdraft, and we showed that overdraft also tends to happen closer to the border than in the bulk. So it wasn't just ground cover, so irrigated crops, it was also overdraft.
Thank you. We have a question from Reem. She says, thank you so much for the informative presentation. My question is, how can this research support early warning systems for depletion of the shared aquifer and lack of compliance with international agreements, particularly in conflict settings?
Yeah, those are two very good questions. I don't think it could replace or even support you know, operational monitoring, right? It won't replace data sharing agreements and monitoring systems that are put in place within the context of cooperative frameworks. So this was not the objective. It was more of an analytical exercise to look at patterns at the global scale. So I don't think our research is relevant in terms of operational early warning. In terms of enforcements, I don't think it is directly relevant either, but maybe one insight that could be helpful is that you should tailor your mode of cooperation in a way that makes it as easy as possible to enforce. And by that, I mean that oftentimes it's more difficult to enforce limits on how much water is being used on volume because you cannot go there and control, right? You could dig a hole anywhere and use water without the other party being able to measure that. But it's easier to monitor where water is being used at all, right? And so I think that was the spirit of those distance-based agreement like the DZ, right? Where they put no limit on how much water is being used, but they put a limit on where the water is being used, which is much easier to enforce. Now, in conflictive settings where you know, you have protracted conflicts and tensions over other issues, I don't think that would be of great help. But when it comes to design cooperative frameworks, maybe it would, right? So in order to kind of design the framework around something that's easy and possible to measure.
Okay, thank you. From your research, we learned that climate change and policy decisions as drivers of hydraulic change are often challenging to disentangle. So based on today's presentation, do you think or the extraction is as a result of policy decisions or policy failures, or is emerging from hydraulic change?
Yeah, well, that's the million-dollar question. I think so. Coming into the research, we thought it was a former, right? We thought it was super interesting, and that it's really those unresolved incentives and strategic decisions and politics that really gave rise to the overuse. Going into the research, as I said earlier, we found that most of this border ward depletion could be explained by river, by geography, by hydraulics, right? Which is somewhat boring, but also hopeful in some ways, right? And so if I had to guess, I would say that most of the effect is explained by geography and hydraulics, which are easier to deal with. But it's certainly not either or, right? I think both really play a key role. So it's a hard question to answer, I think.
Okay, so in last year's presentation, you showed how food security is influenced by water across space. And today's presentation also reflected that most of the extraction is due to agriculture, if I heard you right.
Mm-hmm.
Do you think those areas that are over-extracted is kind of contributing to food security geographically?
That's a very good question. I don't know. Actually, this is a very good idea for future research. Right, so we showed that approximately 30% of groundwater irrigated croplands overlaps with transboundary aquifers. A much smaller proportion really happens close to the border. But what I don't know is where this irrigated agriculture is being used, what is being planted there, where it is being exported. If we implement, restrictive policies on the use of border regions, who will be impacted and stuff like that. I think this is an excellent follow-up, to this research, I think.
Okay, thank you. I'll ask a follow-up on Martin's question. You highlighted different zones, especially the Goldilocks zone. If you are to recommend policy interventions, will it still be on corporations at the national level, or you move down to the local level?
Yeah, I think I would always suggest going to the lowest level possible of corporation, simply because that's an established principle in governance that you should really start at the centralized level. As a matter of fact, if you ask the folks in Geneva who worked on this agreement between France and Switzerland, what they would say is that one of the key factors for the success of the agreement was that this really happened between folks from the city of Geneva and folks from the towns in the French area surrounding the borders, right? So it was really a local level cooperation that was then not rubber stamped, but agreed upon by higher authorities. So for this reason alone, I would always argue that local cooperation should come first. The Goldilocks zone is a bit of a different problem. What we argue is that when it comes to restrictive agreements that are difficult to enforce, i.e., when it comes to restricting how much water is being used, then it could happen, but it really is on a specific area where water is not too valuable, because otherwise there's very little room for negotiation, and it's also not too unvaluable compared to the cost of cooperation. Otherwise, cooperation is not even necessary, so to say, right? But this is somewhat of another story. And we showed that in Geneva, it was right at the right spot, so to say, given the level of trust between the counterparts.
Okay, thank you. I know you're also working on water extraction in terms of critical minerals. And in this current research, do you think that is also contributing to the aquifer depletion beside agriculture? Maybe if the model didn't capture that?
I also don't know. So in terms of absolute volume, it's much lower than agriculture, that's for sure, right? When if you even do a back of envelope calculation on global evapotranspiration associated with irrigated agriculture, is much more than the quantitative water use associated with mining. However, the challenges, the water challenges associated with mining are of a different nature. They're mostly more local and mostly in terms of releasing geogenic contaminants that were previously bound, right? So what usually happens in mining is that you have the mineral that you're interested in that often co-occurs with other minerals that are not good for health or the environment. And so when you extract the minerals you're interested in, you usually leave the other stuff behind, and this other stuff is then mobilized by the water and pollutes, right? And so this is another problem. It's really more kind of at the somewhat local scale. Yeah, it's I don't think that, I mean, I would have to do a study, I guess, but I don't think that mining plays a similar in nature role as agriculture in terms of the depletion of aquifers.
Okay, thank you. I'll end the okay, so what next after this? Maybe in terms of policy interventions or policy briefs or future research. I know you mentioned that briefly.
Yeah, I mean, your idea of following the tracks of borderlands irrigated agriculture, I think is actually a great one. I don't know if it's feasible. We have the data to do that, but I think that would be an excellent question to ask. You know, like let's say that we were to focus on restricting agricultural use in border area in order to kind of smooth up international relations over shared aquifers. What would be the implications of that in terms of food security? I think that's a very interesting question. I haven't thought through yet, but I think it just gave me an idea. In terms of policy, I think the paper I just presented has very potentially actionable outcomes. So there's kind of the average, kind of the aggregated outcome that transboundary aquifer tends to be more used and more depleted, and more used and more depleted closer to the border as well. But that geography plays a key role, I think, should get out there. And the fact that surface water groundwater interaction also plays a key role and could justify the extension of surface water agreement to groundwater should also get out there. But more on a more practical standpoint, I think this typography of aquifers in terms of how intensive their transboundary interaction is, right? So many aquifers don't have any transboundary interaction at all. Some of them have all of the interaction happening close to the border, etc. Like releasing this typography in order to identify which aquifer and which diet of country belongs in which category, I think would be valuable. And thinking carefully about what types of policy would be the most appropriate for which situation. Because I mean, my feeling is that geography often plays an understated role in all those all those usually very legalistic talk about transboundary cooperation with water resources. But for aquifer, it is very, very important, and that should be put out there, I think.
Thank you.
Marc, just two quick questions. One is, how transferable is your finding or comparable are your findings with what's happening in oil and gas fields, right? Share things near borders, because that's always a case that is very interesting and some similarities are there. So if you haven't looked at those, just take a look, because I think there are lessons or parallels to learn from. The other one is, what happens in the cases where you have both a shared aquifer, like, groundwater extraction upstream can be used as a means to affect the surface water flowing into a neighboring country?
Yeah, no, those are two very good questions. And we so on the comparison with oil and gas, I think that's a very valid point. My personal opinion is that there are very fundamental differences that explain why usually there's wars about about hydrocarbons, but not about water, right? So it has to do with private industry and stuff like that. But maybe it's a discussion to be had over beer. But that being said, your point is well taken. Maybe there is some deeper research insight about that. When it comes to upstream downstream interactions over groundwater, this what we actually left it out of the analysis with repugnantly, because I know it's a very important factor locally in some aquifers, but we weren't able to account for it in our analysis. I have specific cases in mind where you could, so to say, cheat on surface water agreements by overusing groundwater. And I think this is a very important needed focal points on the policy development. And happy to talk offline about a brief or something on that.
Wonderful. Thank you.
Thank you again, Marc, for such a thought-provoking and inspiring talk. And thanks to everyone for the engaging discussion, especially our online audience. This brings us to the end of today's UNU-INWEH Science Talk. And as I said earlier on, all the science talks are recorded, which you can access through our YouTube channel. We'll be back next week with another exciting presentation exploring new ideas at the intersection of water, environment, and health. Thank you all for joining us today, and thank you, Marc.
Thank you very much, everybody. Good to catch up.